Okay, yeah, good afternoon, everyone, and welcome to the second installment of Arend's tutorial on Groove. I wanted to look it up, but in the Groove isn't that actually a song title as well? I'm sure there's a song like that. But I
It sounds quite credible that there is a song like that.
wouldn't be surprised. Okay, maybe I'll look it up in the meantime and let you know afterwards.
Sure.
But anyway, so this is the second part after we've covered most of the more basic features in the first half. Now, obviously, we're looking at the more advanced things, so it's going to get very interesting in a moment, I assume. So please, Arend, take it away.
Okay, thank you very much. Glad to be able to present this more advanced part. I'm using a version now that I uploaded half an hour ago, which is a bit risky. Of course, I might get errors, but that will teach me. And yes, I'm going to jump right in, reminding you of what we did last time. And actually, that was less than half. If you look at the number of topics that I would like to cover. Without more ado, let me also then go back to this point 3 that you see here, which I didn't get around to, but since I want to do some stuff that builds onto that, I want to start there. Okay, which means that I'll do that using an example. Let me just show you the example. This is Groove. Once more, this is an example that shows you some capabilities, extended matching capabilities. So what we have is a network of nodes that are connected using a strong, weak, and middle strength arrows here. And what I want to show you is how you can do transitive closure in a rule. And the idea is pretty straightforward. Rather than having simple labels in your rule, you can have essentially any regular expression in your rule. So this is a rule that says from the node that is labeled in it, I want to reach any node using a path of strong labels and mark that other node good. Okay, so here you see where that matches. It's transitive, reflexive transitive closure, so the node itself is reachable in this way. There's a single arrow to a next node or two arrows to a next node. I'm not sure that this is the version I wanted to show you. Just give me a sec. No. Sorry, I'm mixing up two presentations now, but not to worry. It's pretty similar. Yes, actually, I changed the rule a little bit so that it now only adds good if there's not a good already, which is this exclamation mark plus. So it's a conditional addition, but the idea is still the same. I have a slightly different start graph. Let me set the right start graph. A slightly different start graph, but the idea is still the same. So if I apply this rule, then of course the node that you expect to be labeled good will be labeled good. So that's one thing you can do. Next thing, however, is that you can also combine this with so-called label variables. And this is so this question mark X stands for a label that can be strong, middle, or weak. And it will just get expanded to cover all of those cases. So, and then you have a path of which the first edge has a certain label, and then all next edges should also have that same label. So the question mark X here is the same as the one that you're matching here. So now you can use a strong path, but it must be of length at least one, because otherwise you're not matching this first edge. So this is matching the strong, in which case Y here. Let me check. What did it just do? This is matching the middle path. I would expect there. Okay, I think the start graph is not okay. Let me start again. Now I'm now I'm getting a zoom window in front of my own roof window. Okay. I don't know what you see, but I just had a spurious window there. Starting again with the start graph. This rule here is applicable using for two cases using a path starting with strong, which will, it's a bit surprising what's happening here. So maybe I should stop this part of the demo because what I'm saying doesn't correspond to what's actually happening. Here's the weak path in any case. So it will label this node over here with good because it's reachable through a weak path. Okay. Another case where something similar can be done is using flag edges. Here there's a similar label variable that, however, doesn't match ordinary edges but matches flags. In this case, you can also see that you can further choose which particular flags you want to match. In this case, the label variable name is color, but it matches either red or green flags. Looking at the type graph, you can see nodes can have good flags, green flags, init flags, or red flags, but the rule says I want to match only red or green flags, and then add a flag of the same kind to a node that is reachable through a single strong edge. To demonstrate this, I need a slightly different start graph, the one over here. In which case, okay, there are two cases where you can match. You can say this is a red node, and now the successor will also be matched red, or this is a green node. Sorry, the green node, the next one also be matched green, and so on. And finally, you can do the same thing using types. And that's the last thing I want to show about these label variables. This is a rule that says, and becomes a little bit harder to read, admittedly. This is a rule that says I have a node that is my init node, which, however, might in practice have a subtype of node because my type graph does have subtypes of node, A and B here. So the rule, this node might actually be a subtype, and here's a start graph that shows that. I have an init node that's actually a subtype, namely subtype A. And then I follow a path of strong edges, each of which touches a node that has the same type. In this case, is also type A, ending up in a node. And this hash says this is exactly a node type node and not a subtype. In which case, what I'm doing is creating a new node that does have that subtype and merging it instantaneously with the node that I previously had, which had exactly type node. Now, what does this do? It's a bit abstruse, admittedly, but actually this is type specialization. What's going to happen here is that this node that matched by the second of the one that is reached is specialized towards the type that has been matched on the source node. Okay, so to demonstrate this, here I have something of type A. I can reach this node, which is the only one. No, there's a path over here as well. But so applying the rule will change that node into its concrete subtype A, after which the next node is reachable through a path consisting of strong edges crossing to the nodes of type A. So that will then also be changed into A. Long story short, you can do two things in addition to the regular matching that I showed last time. Firstly, you can have regular expressions on edges that match paths through your graph. And secondly, you can have label variables both for ordinary edge labels and for types and for flag labels. That's the point that I wanted to make here. And I hope that you did follow, although it was a little bit confused at some point.
Can I ask a quick question?
Yes.
So is it obvious in which category this is allowed? This specialization of types? I mean, I can see that operationally that doesn't cause any trouble, but do we have? Are you aware of an actual sort of formalization of that?
Good question. I must admit that I didn't actually think about this. I think that in the category where you have these clan morphisms, where you can actually type graphs, this would work.
Okay. I mean, we have these cases where you have subtyping, rewriting with subtyping, and where you can have abstract types and
yes. But if you have an abstract type, of course, then there's no actual type specialization because the abstract one can't have instances. But yes, there are. I have actually encountered myself useful cases where you wanted to do this. For instance, in constructing flow graphs, you start out with a sort of an abstract flow graph where not abstract in the sense of the one you just meant, but you start with a flow graph of which the nodes are just a generic flow, but while building the graph, you specialize those towards predicate nodes or procedure nodes, and that actually is a case of type specialization. Yeah. I can't say for sure, without having thought about it, whether that actually works, because it's the node merging of nodes that have distinct types that makes it work in this particular case. And I don't know if you can do that in that category. Okay, so that's as far as I can answer off the cuff.
Yeah. Okay, thanks.
Okay, next thing I want to show is nested rules. And this is the way in which Groove actually offers amalgamation, as studied mainly by Gabi Tensor. I think it's maybe 2 decades ago by now. But I want to show this on a couple of examples, to start with the BatteryNet example, which actually is a very beautiful example for a rule of this kind. So let me load the grammar. There we go. The point is you can, in one rule now, express the expected behavior of the BatteryNet. And this is the rule. I'm showing you it straight away. But how to read this? You see these additional, say, red-colored and dashed or dotted nodes. Those stand for quantifiers. The idea is that the top level is always existentially quantified. So normally a rule is existentially quantified, and that's it. Whenever you see here a universal quantifier, then everything connected to that universal quantifier is matched in all possible places. Those can be then there can be further nesting through, in this case, these existentials, which means that for all, well, let's look at the left-hand side, for all places you find that are in places of a given transition, there must exist a token with which that place is marked. Well, the rule then says, if I match that, then that token disappears for all those places. So it must exist and it disappears. The right-hand side is an independent universal quantification, which works in the same way. Now you're quantifying over all output places because, of course, you want to put the token on all output places. So you have this additional structure here consisting of the quantifier nodes that tell you how the nesting works, and the nodes, the subgraph that is actually quantified by that quantifier node is connected through these special at edges so that you know this is a node that is quantified by the universal. If you look at this token and incoming edge, yeah, I'm telling you the token is quantified by this existential. The edge is implicitly then also quantified by this existential because, of course, it can't exist on a level where the token doesn't exist. So I hope that this example makes it possible to follow what's going on. let me just give you an example pattern net. Here, there is a there's one transition that's enabled here. It has two input places, two output places. Both input places have a mark on them, so the rule can be applied. And by applying it, well, it's as you should expect. Oops, by applying it, all the output places get tokens. I can now apply the rule in two different places because two transitions are enabled, etc. So I can play through it, and after applying one of them, here's the token that got to be on that place. Now only one. What did I do? Yeah, there's no two. Again, two transitions are enabled. The other one that I didn't just do, or I can go on here to the original to the top level transition. Okay. Maybe the example is small enough so that you can actually follow. It doesn't have an extremely large state space. At some point it just cycles back to the start marking. So this would be a good moment to ask if I went too quickly or said anything that was unclear. Otherwise, I'll continue with some further refinements of this principle. No questions, then I will show you. So I just told you that for this particular rule, the edge is quantified implicitly by the level on which its target node is quantified. There are cases where the edge must be quantified on a lower level, and I can show you using a slightly modified version of the same grammar. Namely, if I don't use nodes to model tokens, but instead just flags to model tokens on a place. So rather than having a token node that is connected with an edge to the place, there's now a token flag on the place node. This means that that flag is actually an edge, but I want to quantify that flag on a level that is lower than the quantification level of its place. I want to remove the token from the place, but the place is universally quantified and the token is only existentially quantified within that universal. So in that case, this is the solution. It is not really pretty, but it works. So you give the existential level a name and then say that token exists on that level named by that existential. So it's the same basic principle, but now it looks a bit different because the tokens are flags. This is, by the way, a point at which Groove really doesn't adhere to the theory, because edges don't have identity in the graphs in Groove. So there can be only one edge of a certain with a certain name between two nodes. And in this particular case, it's a self edge. There can be only one self edge of a given name on a place. So you can't have, in this representation, you can't actually have multiple tokens on the same place. If I take the same start graph as before, then that is not a problem, because this is actually twice a condition event net, you could say, because there's never a case where a place can have more than one token. So this one gives exactly the same state space as before. But if I take another start graph, this one, if you look at this, then you see that although initially these two places have both one token, if these two transitions both fire, then this place over here will only have one token rather than the two that you should expect. So that is, yes, in some way unfortunate. If I apply this rule now, then the bottom place will only have one token. So that's something to realize if you really hate this, because it's of course doesn't adhere to the theory for either double or single push out. If you use graphs of this kind, if you really hate that, you can actually impose things like forbidding rules that can create such parallel edges, so that at least you stay within the set of graphs for which the double or single push out is well defined. Okay. That's the PetriNet example. I want also to show you that if you combine this with the label variables, you can do graph copying. I just think it's a nice example, so I'm going to show this graph copying consisting of two rules, starting with a rule that copies a node. Now, what does this rule say? It says, give me all nodes. This is quantified over all nodes, such that it doesn't have an incoming copy edge. And I'm creating an outgoing copy edge if one doesn't exist yet. So this combination of green and red is a conditional creation saying do something if it isn't there yet. So it's a kind of a abbreviation of the negative application condition and the creation. So if I start with a rule with a graph like this, it is untyped. So you see untyped nodes here and all sorts of strange things. Then applying that copy rule, the copy nodes rule will just create a copy of each of those nodes. This, of course, doesn't copy your graph. You just copy the nodes, but you also need to copy the edges. And there's an alternative rule for the copying of the edges, which is this one. So this does four things. It first of all takes. Let's look at this part first. This takes any pair of nodes with a copy edge in between. No, I should start here. It takes any edge between two nodes, and here you see the label variable. Then it goes to the copy of those nodes and adds an edge between the copy of those nodes with the same label. And it does that for all possible nodes. This thing over here does the same thing, but now for flag edges, which are self edges. You can recognize them here because they're italic. So it copies over a flag edge to the copied node. And this does the same thing for a type edge. Finally, this part of the rule actually deletes the copy edges, so that after applying this rule, you will have your really copied graph. So if I apply that rule here, and maybe I should rearrange it a little bit so that it's more easy to follow what's going on. So here we have the copies of those three nodes. Here we have the copies of those two nodes. If I now apply the copy edge rule, you will see that, yeah, the edge structure also got copied over. Okay, now you might say there are things I don't like about this rule system. For instance, the fact that this has 4 universal quantifications. Can't you somehow combine that? Yes, you can. This is another version of the same rule. Actually does exactly the same, but now it does everything at the same time at the cost of nesting quantifiers. Here we have a universal quantification over all nodes with a copy edge in between. Okay, it deletes the copy edge, and this is the yes, it deletes the copy edge, and here you see an existential with 3 children. And these 3 children, because they are children of an existential, are interpreted conjunctively. So all 3 of them happen. The existential there is just there for the purpose of having children of the existential, because children of an existential are interpreted conjunctively. So this one says copy over my flag. This one says copy over my type. This one says, or copy over any type or any flag, in fact. And this one says copy over the, I'm saying this wrong. Yeah, so this one actually, let's see. No, this one, yeah, no. This one actually says, take this edge over here and copy it to the edge over here. So, as I said, it does the same thing as before. And just to demonstrate that, starting again with the same start graph, And after copying, you get this one. Then copy edges will do the same thing as before and give you exactly the copy. Now, another thing that might strike you about this rule system as not being ideal is the fact that the rules both are applicable all the time. So if I start again, then copy edge is already applicable. There's nothing to copy. If you apply the rule, then nothing will happen. Because there are no copy edges, it just doesn't do anything. Likewise, the copy nodes rule, after applying, is still enabled. But now it doesn't do anything because the copy nodes rule says the node of which I create a copy may not have an incoming copy edge, and it may not have an outgoing copy edge. So it would be somehow more intuitive if you could specify that there must at least be something that this rule does. And yes, there is a variant of the for all quantifier, which is the non-vacuous for all quantifier. And now it says there must be something to do. So of the pattern that is quantified by this quantifier, there must be at least one copy. So now if I apply the copy nodes rule, then it will not be applicable in the next step because there's nothing to copy. And we can do the same thing for the copy edge. It would be over here for all x of which then so now quantifier over the nodes with a copy edge in between. So for all nodes with a copy edge in between, initially there are none. So here you see that initially this rule is not applicable. If I first apply the copy nodes, now it becomes applicable. I've copied the graph. Now I can copy the resulting graph, etc. Okay, so essentially this is another example showing you how this quantification works. And I've also shown you that children of an existential get interpreted conjunctively. Children of a universal get interpreted disjunctively. And in this way, because you now can build a nested tree of existential, universal, plus a conjunction, disjunction, if you place them correctly, this makes the formalism as powerful as first order logic. You can express any first order logic property using a rule of this kind. Of course, the property itself then corresponds to the matching of that rule, and simultaneously you can actually do something by applying the rule. So you already on the PatriNet example, I think you can see that this is actually can be quite useful. And I know that Reiko has, for instance, played around with Groove and also found a lot of uses. I think that I've been very impressed by the quantified rules that Reiko had produced at some point. They do become harder to read when they get more complicated. There's no denying it. What else? I did want to show you. Yes, I did want to show you the disjunctive interpretation of the children of the universal. Going back to the wolf goat cabbage puzzle, which I hope you remember from last time. Now, last time I had two rules, one of which said cross over with some item in your boat, and the other one said cross over while empty. And yeah, this is just a bit of hacking, so to speak. But now using this feature of disjunctive children of universal quantification, you can actually combine those rules in two. Combine those two rules in one. And this is the rule. So how to read this? The top part says the boat crosses over. The bottom part says an item crosses over. It was on the left bank, but now it gets to be on the right bank. But this is universally quantified, existentially quantified under a universal, and the universal has another way to satisfy it. So this is exactly where the disjunctive interpretation happens. Either this universal, which quantifies over nothing, either it says this must be satisfied, and this also quantifies over nothing. So that's satisfied always. It's just true. So one way to satisfy this top universal is just true, is always satisfied. The other way to satisfy it is by satisfying this existential, in which case there must be an item that crosses over. So you can see that the rule actually has 4 applications. Either you cross empty, or you cross with the wolf, or you cross with the goat, or you cross with the cabbage. And that's all due to this disjunctive interpretation. Not claiming that in this example that's very useful. I just wanted an easy way to demonstrate that this actually works as advertised. Okay. Have I lost you? Are you still there? I switched off your video so I can't see if you're still there.
Yeah, we're still here.
Still with
Yes, very clear up to this point. I was just wondering, in this particular example, could you do something with an optional node here instead and have a similar effect?
Yeah, so you're referring to an optional node, and I will show you that actually works slightly differently.
Okay.
Because that's something I haven't now talked about, but thanks for asking. So you could say, I don't insist on this bottom node. Sorry, that's a variation of the exists X. I can actually quantify the bottom node. Oops, what is happening? Yeah, I can quantify the bottom node like this, but that doesn't do the same thing. And I will tell you why. This says match if you can.
Okay.
And if you can't, then you don't have to.
Okay.
But you can here initially. There are things that can move over. So the case where nothing moves isn't there right now. And because you're now always moving over with an item, you can't even create the graph where there is nothing, but I can of course create it artificially just to show you how that works. Start alternative. If this boat is actually on the other side. Oh, that is not what I wanted. Oops. Start alternative. Again, if this boat is on the other side, if that is my start graph, then the cross one rule, this one, is actually applicable to the boat, although there's nothing that it can take with you. And this is where you see the effect of the optional existential. And of course, after doing that, you're back in the situation where you must always take an item because there is one.
Okay. Good.
Okay. Thanks for asking. Let me see. I think I did cover everything. Thanks to Reiko's question, I actually also covered the optional existential. Otherwise, I would have skipped it. Yeah, I did go through the themes on this slide. So that is what I wanted to show about nested rules. So if there's anything that you're wondering about right now, can you do this? Can you do that? How does this actually work? This would be a perfect moment to ask. And if not, I will continue.
Can I ask something quickly? Maybe this will, I forgot the exact list of topics, but is there any way of converting something like a rule with nested conditions into this particular format? Maybe I missed something. Or is it just an alternative control structure for rules, let's say? I mean, if I'm more familiar with the theory of nested application conditions, for example.
I think this actually is nested application conditions,
right?
And then some, because it's not only application conditions. You can actually do something with the part that you have tested for in your application condition.
And the second question was because after all, this is a tool for specifying a writing system. So if I knew how to specify something like a structural constraints on graphs I want to have enforced, is there a mechanism to convert this into sort of a constraint preserving condition on a rule in this calculus?
No, it's a very interesting question, but this is not among the things that, well, I mean, let me separate your question into can it be done theoretically and can it be done in this tool?
Yeah.
Theoretically, there is theory that will actually construct rules for you by shifting conditions over rules. They tend to become more and more complicated. I think that Karl-Heinz Pennemann did a lot of work. So did
Oh, no, that part I know, of course. Yeah. No, the question is about implementation. I mean, let's say I know the constraint preserving condition in nested application condition format, even in some reduced form, perhaps. Could I then translate that into your tool in some?
There is no support for this.
Okay.
So that might be something to work on actually, because I think it would be quite interesting to have, but I tend to especially do things if I have users for them.
Sure.
Declare yourself to be a user and want to do it. Yes, by all means.
Yeah. Maybe we can discuss more at the end of the talk. I let you move on, of course. Yeah.
I said this was wanted to tell you about quantification, but it's not quite true, because there's actually also some second order features that are supported. And what do I mean here? Well, you can count and you can apply some set-based operators. Let me start with the counting. So here, this is a flower market. You have geraniums and fuchsias, and they can have flowers or not, and they all have a price. So that's the setup. And here you see that you can actually count. So this actually quantifies over all flowers. This quantifies over all plants that have at least one flower. That's what you see this non-vacuous universal quantification. So, and this tells you flower.count, and a flower is the name of the universal, and flower.count is the number of matches that are found for this universal. And similarly for a plant, so you're counting both the number of flowers and the number of plants with at least one flower. And just again to show you that it works, here we have 3 flowers and 2 plants with flowers. And if you apply the rule, I think I applied a different rule. No, I did apply the right rule. Where is my the base flower count? That's not flower count. This is odd somehow. Oh, there it is. Yes, here we are. It was. We have just counted in the expected way. So that's one thing. The other thing is that you can apply set-based operators, and this is an example of that. You have a basket that was already there, but it was out of view. So here's my basket. And this says, for all the plants that are in my basket, I want to sum up their price, and that will be the amount that I have to pay for those flowers. Now, originally, there are no plants in my basket, so let me put some plants in my basket. There we go. There's a geranium in my basket, and there's a fuchsia in my basket. Now, if I want to pay for the geranium and the fuchsia, then that would be 2.5, right? So, yeah, 2.5, great. So the idea is that you sum over all the prices of the plants that are universally quantified. So this exists for summation, because summation is commutative and associative. So if you have a set of prices, which in this case are real numbers, if you have a set of real numbers, then you can say sum up. You can't say subtract, because that is not meaningful. You can say multiply, and so there are also a number of operations over booleans that have this property. So for those operations, you can shortcut, and this actually is quite a powerful thing if you are in the situation where you can use it, because if you would want to do this without this particular feature, then you would have to sum them up one by one, and they don't have an order, so you then have to find an order to sum them up. If you're not careful, then you're going to go all possible interleavings or orderings of summing them up. The effect would be the same, but taking a whole lot more time and intermediate states to get there. Okay, this now really is everything I wanted to tell you about nested rules. So next thing, the next large topic is control. And to start with control, I want to first talk about rule parameters. And I want to do that using an example that I used last time as well. The game that we had, and just to remind you, the game consisted of having a pawn that walks around on locations and a die that tells you to throw certain values. After having thrown a value, the pawn moves that many steps as the value that you have thrown. I have changed the rule system a little bit, so it now consists of essentially 3 rules, saying you throw, and the throw introduces a throw node with a chosen value, which is one of the possible i's value of the die. Then there's a subtract rule that subtracts 1 from the throw, as long as it doesn't, as long as it's not 0. And there's a step rule that moves a pawn from one location to the next. What I have the last time around, the subtract and step rule were combined in one rule. Now I've pulled them apart, but in order to make sure that they are still happening. Sorry, I'm sorry. I'm now presenting 2 things at the same time. I wanted to present them one by one. So let me present them one by one after all. First, I want to present the notion of a parameter. And the notion of parameter involves exposing some of the match on the rule label. In particular, here you see that I'm throwing an i's value, but I don't know which value I've thrown. And that you can expose using such a parameter. So this is done in the following way. I declare the parameter. This is an int, and it is actually d.i's. And this then, okay, I have to name this. And here I say the value becomes val. Now you see on the left-hand side, this adornment over here tells you that's the parameter, and parameters get exposed on the rule on the transition label. So they're actually part of the match that you can see from externally. And now you see that these parameters can be distinguished already at matching time, which of course makes it much more easy to follow what's going on here. Similarly, the move rule doesn't tell you which pawn has moved. Now, in my original setup, there was only one pawn, so there is not really a choice, but I can change the start state and just introduce a second pawn. At which point you don't, either of them could have moved, and you can't see which one. So if I throw the value 2, then I can move this pawn over here. I can move this pawn over here. If I look at the transition system, I just see move. I don't see what's happening. So similarly, this can be solved by introducing a parameter on the pawn. In the same way, just say par 0, 0 being the parameter number. Rules can have more than one parameter. But now after throwing 2, you can see either I move node number 7 or I move node number 8. And after move node number 7, I can choose to move the same pawn again. So now in the rule system, in the transition system, you can actually see it's exposed on the transition label which pawn has moved. Okay, so that's step 1. That's actually the idea of having parameters in the first place. Having these parameters, you can also use them to actually input values into your rule system. Here, there's a rule that says I have two distinct persons and a new person gets born. And the new person needs a name. And a name is given to the rule system through a parameter. This star here means it's an ask parameter, which means that when the rule gets applied, I get somehow the feeling the value for it from outside. How I get it from outside is actually can be controlled through what's called an oracle, which is set in the system properties. So right now I'm saying my oracle is a dialog, which means that if I try to apply this rule, then I will be asked for the name of the node I want to create. So let me say I'm going to create or to give birth to a Raiko. Then I get a person named Raiko, who is the child of John and Mary over here, and so on. So that's the idea of these ask parameters. However, you can also use a different way to get those values. In particular, you can say, I want to read them from a file. So that is a different oracle. You specify input and then the name of the file. I prepare the file name.txt, names.txt. It's not called input, it's called reader. Reader names.txt. So I can show you, this is the names.txt file. Raiko, Andrea, and Barbara in that order are specified, and you see that I omitted the quotes around Barbara on purpose, just to show you what happens. So the first person born is still Raiko. The next person born, but they can have multiple parents. But the next will be Andrea, and then the fourth person born will be Barbara, except that my file didn't specify a value. I forgot those quotes. So it says this is NAS for not a string, and I'm now in an error state. This is just to show you how these errors are being handled. Okay. Main message here is this is a way to actually get some external values into your rules through these oracles. You can also, there's two more oracles. There's a random oracle and there's a default value oracle. And let me check what happens if you do random here, and a random name gets generated. Okay, here it is, random name. Well, I think you get the idea.
Can I ask a quick question in between? So your example with the dice, so could you specify somehow you want as input some number between 1 and 6, but with a uniform probability?
That would be nice, and it's almost there. No, actually that works. I think I made an extension for which that should work. Let me check. So I think that works. Or let me check it over here. I'm just going to create a rule that says, give me a node. Yes, so random. Type node. And or I'm going to create a new node with an X value is some R, where the R is randomly generated. So that is an int, an ask parameter with the name R. Okay, but that's not all I want, because I want to constrain this int. So I want that it is R is I'm not sure this is going to work. Okay, I'm going to type it and then show why it doesn't work. No, 0 is smaller. No, let's say that R should be smaller than 7. Yeah, it complains actually. It says this this can't be done, or at least Groove doesn't support it right now.
Okay.
What you can do is, I think you can do the following. You can generate instead a reel, but you can't constrain the reel. What you can do with the reel is say, I want to multiply it by 6, and then take the upper bound. Now I have to look what if the upper bound exists. Yeah, you just convert it to an int. Yes. Okay, I'm going to do like this, multiplying r by 6 and then converting to an int. Yeah, this is a bit of. This is interesting. Now I don't know what's happening. This is actually, I can't identify this. This looks like a bug to me. The idea, I hope you see what I'm trying to do at least. Unfortunately, I don't think I can make it work right now. I'm generating a reel, so now the reel is unconstrained, so I don't have the same problem as before. I should be able to multiply it by 6, which gives me a number. So a real random number is somewhere between 0 and 1 by default. So 6 times 6 would be between 0 and 5 inclusive after chopping it off. In other words, converting it to an int. But I'm not sure what this error means. Okay, this is not the moment to start debugging Groove, I guess. I see that I'm already, getting quite close to the hour mark.
Yeah, just carry on. Thanks anyway for answering.
Yes. Yeah, no, thanks for the question. It's just I get over enthusiastic about this thing and just spend too much time explaining stuff. I showed you parameters. Let me now show you actually how you can control rule applications. So now I'm going to go back to this version of the game where the rule of stepping and subtracting is split in 2. Of course, now after you throw stuff, if you're not careful, then after you throw stuff, you can just continue subtracting without ever moving a pawn. Clearly not intended. Instead, what I had in mind was that after each time I subtract, I do a step. This can now be specified using a control program. And this is the control program. What it says is, as long as possible, do a throw, then as long as possible, do a sequence of subtraction and steps, and then 0, which means test for zeroness. And if if it is 0, then I remove the throw node. Now the test for zeroness actually isn't here, and that is because I did the subtraction as long as possible, and as long as possible means I continue doing subtractions until the test is violated. In other words, until the value is 0. So by virtue of this control, now I can simplify my rules. So in general, the point of control is actually to, I would say, remove some spurious information, to remove information that otherwise would be encoded in your rule and move it to the control program. So in all cases where you already have a rule system that works without any external notion of control, you see that there is special structure in your graph that is only there to ensure that rules get executed in the order that you have in mind. Now, that is then not part of, say, the conceptual problem domain, and you can introduce graph structure to encode that desired order, or you can do it using control like this. Maybe to anticipate the question that you might ask, I don't know of a general way to convert from graphs without control to graphs with control. I'm pretty sure there is a way to convert a graph system with control into a graph system without control. Although, now I'm thinking about it, it's probably not at all trivial to do that. Okay, Groove offers you this way to do things, and with this rule system imposed, or the control program imposed, things only can happen in the order that you intend. So you have to start by throwing, then you have to subtract. You can't move right now. You can now step, you can now subtract, you can now step, and now the value is 0, so you can do 0. So this is again back to the intended behavior. Can be combined with parameters in the following way. Suppose that I have a board with 2 pawns, and suppose that actually the rules tell me that I have to use the same pawn all over and over again, and I can't use my throw to move one pawn in 2 moves and the other pawn in 1 move if I've thrown 3. If that is what you want, then you have to remember which pawn has moved, and you have to ensure that the next time around you move the same pawn. So this can, of course, again be done using additional control information in your graph, but you can also do it in a control program like this. This is a variation where rather than subtracting and stepping, you first select a pawn that you want to step with. The selection here is a rule that I didn't show before, is this rule. This rule only matches a pawn and has it as an output parameter. And in the control program, that output parameter gets assigned to a node variable. The step rule now can only be applied for that particular pawn. So this ensures that you're stepping with the same pawn. Okay, so now you see, oops, why is this? Oh yeah, this actually gets quite big because I have 2 pawns and they can have, combination of places. So this is a bit too large to actually make sense of visually anymore. It doesn't even show you the entire state space because I've restricted it to 200 states. It's still 200 states, but now it's 2000 states. This is the entire state space, yeah. Obviously too large to still make sense of visually.
So very briefly, when you have such a system with control constructs, in particular loops, so then the state space, does that mean you explore all possible paths when there is non-determinism in the rule application?
Yes. Yes.
Okay.
Yeah. So that can be seen, I think, here. Well, maybe I should start over again and say. I mean,
then it's not surprising it's getting big, right? As soon as you have loops.
No, it's no surprise it's getting big. Absolutely. Here you see that after throwing, you have the selection of the choice of selecting between 2 next states. Yeah, so that's the pawn you select, and after selecting a pawn, you can only move that pawn. So you subtract, and then there's only 1 pawn that can be moved. It's the one that you selected before. So you can actually see the node identity, which is 7. But yeah, there's this choice initially, and all paths get explored if you do the full state space exploration.
Okay.
Next refinement here is, suppose that I have this start state over here. Now the board has changed, and there's actually a path that leads nowhere, which means that I could get stuck in the middle of my move. If I throw 3 and I use this pawn, well, this one only has 1 pawn. If I use the pawn, I go to this state over here that I can't even finish my 3 moves. Well, that might be the intended meaning, but you might also have had in mind that you only make choices for which you can actually finish the move. And now this can only be done using some sort of look ahead, and that look ahead is provided in Groove by so-called atomic blocks. So I can say this whole atomic block in the as long as possible, with the whole body of the as long as possible should be executed atomically. I added atomic brackets around them, which means that this now suddenly got a sort of a transactional behavior, all or nothing behavior. I can only finish the I can only say finish the body if I can finish it entirely. Now, this you might wonder how that works. So if I throw, then there's only one to select, subtract. Yes, subtract, come on. Then step, subtract. And I want to go this way. Subtract, and now I can't step. How does that work? Well, I didn't enable this control, so the one that I added the atomic block to should be the one that I should have used. So let me do it again. Subtract, step, subtract, step in the wrong way, subtract, and now I can't step. The rule system now declares the states that I reached to be absent. They are still shown, but I can also hide them from view so that they're really invisible. And it considers absent states to be well, mistakes in expiration, and it then backtracks to the state where this one, where the first absent state was reached. You see that it's now crossed out, the only really possible one being the other one. And during full state space expiration, you get a lot of absent states, but you can then say those are not the ones that I'm interested in. I actually don't want to see them in the first place. So although, of course, you have to detect this first using expiration, it then rolls back and pretends that those paths that can't complete an atomic block simply don't exist in the first place. So that's quite, I would say, a powerful kind of control that I think is beyond what is usually offered in this context. And to take it one step further, and now it really gets very powerful, I would say, you can wrap this into a so-called recipe. And a recipe is by default atomic. So this recipe is a move. It has the same internal structure as the atomic block of the as long as possible of the previous recipe. But now the recipe is actually considered to be one transition. And I want to start by showing you all the internal steps of the recipe, including the absent ones. What is happening here? Did I actually get a crash? I'm not seeing anything, so it looks as though something crashed on me, which is not nice. Yeah, something crashed on me. Why? Okay, this is something that I, again, can't figure out on the spot. I'm going to restart Groove and hope it doesn't crash again. That's the danger of course, trying to make last-minute changes to make things more beautiful. Yeah, come on, we can do it. Nah. This is a pity. I'm going to use an older version of Groove because this is apparently I did something in the last minute that made it crash. There we go. Same story, it looks a little bit different on the left-hand side, but the idea is still the same. So here the expiration gives me a lot of red-colored states that are the internal states of the recipe. But if I hide all of those, then I get, well, essentially this is the entire behavior of the game, where the transitions correspond to complete executions of of that recipe. So I have a complete move here, which underwater corresponds to a sequence of throwing, subtracting, moving, etc. So now this gives you the ability to declare what essentially behaves like a rule, but actually underwater is a recipe. So which underwater does a lot of stuff, but in the transition system just exposes that at a single transition. Unfortunately, I'm now forced to use an older version, which doesn't show all the goodies that that I wanted to show. So maybe it's a good moment to actually stop also, because I think I've also overrun again. The last thing I had on my agenda was to show you also the model checking. And I think I can do this quickly to give you a very general idea. So if you don't object, then I want to do that. I can't see if you object, so I'm just going to do it.
Yeah, go ahead.
At the same time, I want to, the reason why Groove now crashes in the development version has to do with, I don't know exactly, but it had to do with the rule system. It tried to load the rule system on which it crashed, and it's going to continue doing that. So I have to now disable that rule system so that it can't load it and can't crash, which is easily done. Hope. Just revert. Select all. Okay. And restart. Is it restarting? Yes. Okay. For the demo of the model checking, I'm going to go back to the wolf, goat, and cabbage puzzle once more, with the two different rules and one condition that says mealtime, which means that one item can eat the other because the boat is not around. And this is, of course, what you want to avoid. So the full state space, well, that looks like this. It's not all that large. But what I want to know is automatic. I want to automatically find out whether there is a winning strategy. And this can be done using linear time model checking, for instance, by saying the state in which the finish condition holds is not reachable. So this, of course, is not true because the finish condition is reachable. And what LTL then does is to provide you with a counterexample. So here we see the counterexample to that condition, which is now highlighted. I'm not sure that this is actually the version that I wanted. Sorry. Sorry for this demo effect. I'm just going to do it again because we didn't quite get what I expected. Okay, verify finish is not reachable. Yeah, this is what I expected. So it highlights the path to a finish, thereby showing that it is reachable. The path is a bit longer, but that's just due to what model checking does. However, the solution it's giving me isn't the one that I wanted, because it passes through a state where mealtime is allowed, and that's what I want to avoid. So I can refine that by just giving another property, this version says there doesn't exist a path that ends up in finish and globally does not enable mealtime. So the path that I'm denying the existence of is one that reaches finish without ever enabling mealtime. And that turns out that the property doesn't hold. Therefore, I get a counterexample, and therefore, and that counterexample will satisfy well, the conditions that I'm after. And here you see it. So you're going, well, you can't read this, but you're loading something, you're crossing empty, you're loading something, you're loading something, you're crossing empty, and you're loading something, which is, if you know the puzzle well, you realize that this is the way to do it. If the some things are the right things. You can also play it through here. The start ones are the transitions that you want. So you're crossing with the goat, then you're crossing empty back, then you're crossing with the wolf, you're crossing back with the goat, you're crossing back with the cabbage, you're crossing empty, and no idea why it enables two things here. Interesting. I would expect that the solution is to cross with the goat. Yeah, there we go. Now we have the finish condition. Right, so this is to demonstrate that Groove has LTL model checking built in, and this can be used to find counterexamples to properties that you're entering. It also has CTL built in. Well, CTL is a different logic where you can express different things, and the whole notion of counterexample becomes a whole lot more complicated. So you don't see much, but you can check for instance, you can say along all paths eventually finished. And if you think about it, then in this particular rule system that holds, but that's just because it doesn't hold. Interesting. Of course, I know it's not just because there are paths where finish is never reached. Instead, if I say along all paths, there is a path where eventually finish, then yeah, this is always true. And it is always true because nothing actually gets eaten. Here I'm saying, yeah, something could eat something else, but it doesn't actually eat it. I could modify the rule by saying it actually gets eaten. So this item goes away, and then I expect that property to no longer hold. So same property. Yeah, now it says it fails to hold in the initial state. Okay. LTL is often preferred by people exactly because if it tells you that the property doesn't hold, it tells you why it doesn't hold. For CTL, that's a whole lot harder because the strategy, it actually evolves more like a strategy rather than a single trace, and Groove doesn't give you any support in that sense. Okay, I think I used up my time and then some. So let me stop here and thank you for listening, and see if there are still more questions, if there's actually still people around and they have questions.
Yeah, there's still some people around. Well, thank you very much, first of all. That was a very nice overview.
Thank you.
I recognize much of it, but not everything. So there were still things that were new to me. So that's
okay, good.
Been sort of
There's
playing.
also things that I didn't demonstrate, by the way. Among other things, very recently introduced a notion to define user-defined operations.
Oh yeah, I saw that. Yeah,
The
I haven't time to try it yet, but I saw the.
Yes, so that's something that Reiko had asked for, and it is there, but it still needs to be tried out by somebody else than me.
So the background for that, I mean, or one of the backgrounds that may be sort of interesting to Detlef, because he was asking similar questions. I was basically interested in generating random numbers inside Groove, and obviously one way of doing that is if you have I mean, there are random number generators in Java, and if you can use external functions, then you can basically use those existing ones rather than having to implement something like that in Groove itself. I mean, to some extent, maybe it's possible in Groove itself if Arend can work out what went wrong in that particular example, but certainly one way of looking at this, or one way of doing it, would be to use existing implementations. So that was the background anyway for that question.
Yeah.
All right, but yeah. So any questions?
Just one brief comment on what Reiko just said on the, you could do this with these variables, but what we did in GP2, so I had one PhD student who did evolutionary algorithms. And of course, you need randomness there. It's at the core, right? But rather than having some ad hoc construct, we really defined a whole new version of GP2 called PGP2, so probabilistic GP2. And there you have genuine constructs where you can properly do some form of probabilistic programming. So it's always the question, do you want to put everything into the standard language, or do you have perhaps a variant which is dedicated to a probabilistic setting? So just as a quick comment. So.
Yeah.
But that is a step further, isn't it? Because you support probabilistic choices between.
Yeah, you can control your choices and with
between
what
matches,
probability, what
between
rules,
different matches, between rules and things like that.
Yes. Yeah, it's clear, I think, from what I presented and the way I talk about this, that I tend to want to put everything in a single tool. The probabilistic exploration, the kind that you're talking about in this tool, would appear as a sort of exploration strategy, which I think I briefly mentioned during the last talk. You can actually explore your transition system in different ways, and this doesn't out of the box support much. There is just breadth first and depth first and linear, and actually the LTL strategy is one of those. But there is indeed where you would like some control over which of the possible matches you're going to explore, and certainly if that's going to interact with the actual graph structure, that gets beyond what you can easily do in Groove.
Yeah, I mean, you would also get into the realm of probabilistic model checking, I suppose, if you wanted to do that seriously, which I mean is an interesting thing, but it's not a different kind of algorithm, I suppose.
Yes.
You have to use for that. I'm not an expert, but I'm sure it's different. Okay. Any other?
If I can comment on one topic, Arend, I think could be of some interest to elaborate or to think about what you mentioned, the possibility of finding an automatic way to translate the external control into a graphical representation.
Yes.
Okay. Yes. So accepting the fact that there are systems or formulas which are based only on the default mechanism of applying in all possible ways sets of rules, and those which are instead equipped with some control language that is more or less always the same more similar to GP2 and the one that you presented and so on. Concerning these, and I don't know if it could be interesting to explore this. There is the point of transactions that you introduced. Okay,
Yeah.
you said it's useful to have transactions, and I definitely agree to not be able to interrupt some evolution which is defined by rules in a fine-grained way, but you would not like to interrupt it in the middle. You would like to be sure that you arrive to a consistent state. And on these, we worked several years ago with Leila and a student of Leila about enriching graph transformation system with transactions, but without having a control structure, an external control structure. So I'm trying to understand, how do you model transactions if you only have the standard rules and you apply them in any order? And we came out with the idea that since you don't have external control, everything has to be represented in the graph, right, in the state. And therefore, we considered this generalization of the so-called zero-safe Petri nets by Roberto Bruni and Ugo Montanari. The idea is simply to have part of the type graph which represents entities which are in a sense unstable, which are temporary. Okay, so if in your graph you have something which is typed on this part of the type graph, you cannot stop. This is not a stable state. You are forced to go on and up to the next state where you don't have these parts, and this is considered a stable state. So this was just an idea to mimic the fact of having states which are not stable and stable that you can define using transaction. I was just wanted to mention this.
But you're saying that this is not, that there's still things to be figured out in that context. It's not finished work.
No, this work was dismissed. We didn't we defined the transactions in this way, then we didn't work anymore on this topic. I don't know if this could be interesting to try to approach in a systematic way, this idea of transforming control to transferring external control to graph, to the graphical way of controlling. The vice versa, as you say, this is not clear at all. If you can extract in some automatic way from a set of rules, if you can extract in a systematic way some external control changing the rules.
Well, I'm fairly confident that you can go quite a long way. And the reason why I'm confident is that this actually, the things that Groove does is actually implemented by constructing a sort of control graph that is then say paired with the actual graph, and this control graph I think has states that are labeled transient, and that is essentially, I think, the same concept of what do you call it, unstableness that you mentioned. So if you put that information into your actual graph, I think that you might already be reasonably close to.
So you mean transferring the external control to a graphic? Okay, yes. I agree that this is something should be feasible. Yes.
So I can just maybe say what I find interesting about this is that, I mean, what Andrea did with Leila, it basically shows that the notion of transaction doesn't necessarily depend on control, because there the transaction works in a data-driven way, as long as there's temporary data or sort of unstable data, elements of unstable types basically in your graph, the transaction isn't finished. So you have a way of defining the start and the end of the transaction, but you don't actually have a control structure. It's sort of makes these things orthogonal in a sense. So that's what I found. That's what I found interesting. Whether it's the best way of doing that from a language point of view is another question. But
okay. We just identified something that we can work on, Andrea.
Yes, in fact, will be very interesting.
Yeah, I'm going to come over to Pisa in 2 weeks, or less than 2 weeks.
Oh, 2 weeks
Less
already.
than 2 weeks already. Oh,
It's yeah. I'm going to ask you next in a week from now. Where can I show? Where can I sit in? Which office? Do you have an office for me?
I say have a seat in an office, not
But maybe
not
a
an
desk.
entire office, but
Nice.
I'm sure about this. Okay, so we will have to speak about this logistic stuff, also the other aspect. Okay.
I don't know if this is still
Right.
live, by the way, Nicolas.
Maybe if you're at that stage, we can close the official part
Yes.
of the seminar now, because maybe the YouTube audience is not interested in domestic arrangements or office arrangements. So yeah, so thank you very much again, Arend, and good that we brought that to a satisfactory conclusion in the end. I don't know how much you left out, but maybe not too much, I hope.
Well, I've obviously am quite annoyed about the bugs that I ran into.
Yeah.
But I hope I managed to get across the ideas despite the hiccups.
Yeah.
Right. Well, thanks a lot, Arend. And I'm just going to close the YouTube stream. If anybody still wants to come over, you might stay for a few minutes, but not. See you next time. Thanks a lot again, Arend.